All right, welcome to The Explainer. Today, we're taking a really deep dive into the invisible mechanics of local networks. If you've ever wondered exactly how a message gets from your phone to your router without just getting completely lost in a sea of invisible signals, well, you are absolutely in the right place. Whether you're studying for your CCNA, diving into cybersecurity, a system admin, or a software developer, we're going to unpack the exact rules and hardware that make local networking possible. And we'll keep it simple, starting with some intuitive concepts before we get into the technical nitty-gritty.
So, here is our game plan. First, we'll establish exactly what the data link layer is. Then, we'll look at frames and MAC addresses. Next, we're going to see how network switches actually work under the hood, followed by traffic control and collisions. After that, we'll hit some advanced Layer 2 concepts, and we'll wrap the whole thing up with some real-world network troubleshooting scenarios. Let's get to it.
Starting off with Section 1, the data link layer.
Okay, so you're probably familiar with the good old OSI model, right? That 7-layer framework explaining how all network communication happens. Down at the very bottom, Layer 1, the physical layer, that's dealing with raw electrical signals or bits over a wire. But right above that is our focus for today, Layer 2, the data link layer. It acts as this absolute vital bridge between those dumb physical cables at Layer 1 and the smart IP routing happening up at Layer 3.
To truly grasp this, let's use an analogy. Think of the internet like a massive apartment building. The IP address? That's the address of the building itself, making sure the mail carrier gets to the right street. But once the mail is actually inside the lobby, how does it know which specific apartment door to slide under? That is the data link layer. Technically speaking, it takes those raw bits, organizes them into meaningful chunks called frames, and ensures reliable local delivery using physical MAC addresses. Realistically, when your laptop talks to your home Wi-Fi modem, they aren't using IP addresses to talk directly to each other over the airwaves. Nope, they are communicating exclusively through Layer 2.
Moving right along to Section 2, frames and MAC addresses. Data doesn't just flow out into the ether randomly. It gets neatly packaged into what we call a frame. Think of framing literally like putting a letter inside a sealed envelope. Under the hood, this frame has three main parts. You've got the header, which contains the source and destination addresses. Then you have the data, which is the actual payload, the letter inside the envelope. And finally, the trailer, also known as the frame check sequence, which acts like a tamper-proof seal carrying some clever mathematical error-checking information. Now, look at that number on the screen, 48. That is kind of a magic number in Layer 2. When we talk about addressing in the frame header, we're talking about MAC addresses, or Media Access Control addresses. A MAC address is exactly 48 bits long, and we write it out in hexadecimal format. Unlike an IP address, this is a physical, hard-coded address permanently burned right into your device's network interface card, or NIC.
It is incredibly crucial to understand the difference between an IP and a MAC. To put it simply, an IP address is like a zip code, while a MAC address is like your specific desk in an office building. At a networking level, an IP address operates at Layer 3, and it changes entirely depending on what network you connect to. A MAC address operates at Layer 2 and is physically fixed to your hardware. Say you take your phone down to the local coffee shop. It gets a brand new IP address from the shop's router, but your phone's MAC address? That remains exactly the same.
So how big can these frames actually get? Well, a standard Ethernet frame carries a maximum transmission unit, or MTU, of 1,500 bytes. That's your standard payload limit. But if you're dealing with massive data transfers, network engineers can configure what are called jumbo frames. These are much larger, and they give you higher performance because there's way less overhead on the network.
That brings us to Section 3, how network switches work.
To really appreciate a switch, let's contrast it with an older piece of tech called a hub. Picture a hub as that one annoying coworker with a megaphone, just shouting your private message to the entire office. It blindly copies data to every single port, which causes massive congestion. A switch, on the other hand, is like a highly efficient mail sorter who discreetly hands the letter directly to the right person. It does this by reading the source MAC addresses of incoming frames and dynamically building a MAC address table in its memory. It literally links specific physical devices to specific switch ports.
Because modern switches are so smart, they can juggle different types of traffic. Unicast is your standard one-to-one conversation. Multicast is one-to-many, kind of like streaming an IPTV channel to a specific group of TVs. Broadcast is a literal shout to absolutely everyone on the local network, and the destination MAC for a broadcast is literally just all Fs. But here's a fun curveball. What happens if the switch gets a frame for a unicast address it hasn't learned yet? That's called an unknown unicast. When that happens, the switch temporarily acts like a hub and just floods the frame out of all ports to track down exactly where that mystery destination MAC is hiding.
All right, Section 4, Traffic Control in Collisions.
Let me ask you this. What actually happens when two devices try to talk on the exact same wire at the exact same millisecond? It's an important question. If two devices send electrical signals down the same copper wire at the exact same time, the signals crash and scramble each other. We call this a collision. To prevent total chaos, networks need some really strict traffic control mechanisms.
For wired Ethernet, the solution is a protocol called CSMA/CD. The absolute best way to visualize this is like a really polite conversation at a dinner party. Before you speak, you listen. If someone else is talking, you wait. If there's a pause, you talk. On a network level, if two devices happen to talk at the exact same time and they detect a collision, they both immediately stop, wait a random fraction of a millisecond, and then try again. It's elegantly simple.
But what about Wi-Fi? Well, this brilliantly illustrates the difference between physical mediums. Wired networks use collision detection because a physical device can literally feel the voltage spike on a copper wire. But on a wireless network, which uses the 802.12 standard, detecting radio collisions in thin air is nearly impossible. So Wi-Fi uses CSMA/CA, collision avoidance. Wireless devices actively coordinate and literally reserve airtime before they transmit, purposely trying to dodge crashes altogether. Now, even if there are no collisions, a frame can still get corrupted by random interference. This is where that trailer on our frame comes into play, using a cyclic redundancy check, or CRC. Remember how I called it a digital tamper-proof seal? Here's how it works. The sender runs an incredibly complex, exact mathematical calculation on the frame's ones and zeros and attaches the answer to the trailer. The receiver gets it and then does the exact same math. If the answers match perfectly, the data is perfectly safe. But if it's off by even a single bit, the receiver instantly rejects the entire corrupted frame. No second chances.
Moving into Section 5, Advanced Layer 2 Concepts.
Probably the most common tool in a network admin's arsenal is the VLAN, or virtual LAN. Imagine taking one massive physical switch and using an invisible force field to slice it into two completely separate mini-switches. This gives you brilliant logical network segmentation. For instance, a company might put all the accounting department computers on VLAN 10 and the IT department on VLAN 20. Even though they are plugged into the exact same physical box in the server room, Layer 2 isolation means they literally cannot see each other's traffic at all.
And to make these VLANs work, a switch uses two different types of ports. An access port connects to an end device, like your PC or a printer, and it belongs to only one single VLAN. But when you need to connect two switches together, you use a trunk port. This port tags and carries traffic from multiple VLANs simultaneously across a single cable. Oh, and as a vital safety measure, when connecting multiple switches, engineers use something called Spanning Tree Protocol, or STP. STP is the unsung hero that intelligently shuts down redundant links to prevent infinite network-crashing broadcast loops. It is a total lifesaver.
Finally, Section 6, Real-World Network Scenarios. Let's put this into practice.
When a user inevitably complains that they cannot reach a website, a good network engineer troubleshoots using the OSI model from the bottom up. First, Layer 1. Is the cable actually plugged in? You'd be surprised. Next, Layer 2. Are the MAC addresses resolving? Is the switch port active? And is it on the correct VLAN? Then, Layer 3. Is the IP routing correct? You see, only after systematically clearing the bottom layers do they check upper layer issues like blocked transport ports or failing DNS servers. You have to build the foundation first.
Ultimately, the data link layer is the true unsung hero of our digital lives. It takes the absolute chaos of raw electrical signals and radio waves, packages them neatly into organized frames, slaps a physical address on them, and navigates them safely through a maze of switches. So the next time you connect to a network, take just a second to wonder, what exactly is the switch doing with your MAC address right now? It's pretty fascinating stuff. Thanks so much for joining us on this explainer, and we will definitely see you in the next one.